Okay, everybody. Good morning to you. I hope you guys are doing well. Let's see. Okay, yeah, you do have my audio. My audio is there. Our audio is there. So, how you guys doing? You're doing good? Okay. Well, let's go to the browser. We're going to continue our discussion on probability distributions here. Okay, so I'm going to go to Math 227. And in Math 227, we're going to go again to the Statistics Online Transition. So I'm going to look for the normal distribution, normal probability distribution here. I'm going to give you guys some notes here. So I don't know, do you guys go back and you guys download some of those notes? Just curious. Because a lot of my students in the past, that's what they do. They've done that. And they've said, thank you for those notes. So I'm just kind of worried. I'm sort of curious if people here are also making use of those notes. I mean, if you're present, you can always go back to the video and download that link, or you can even watch where I get it from, right? So hopefully you guys are doing some of those kind of things. But I'm going to go to the iPad personally now and download those notes too, so I can import this. All right. All right. So as I'm doing that, let's see. Gotta wait for the internet. La 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 la. And you guys can see what I'm doing. Well, maybe you can't. Create a new note. I'm gonna create a new note. It's gonna kind of give some weird. Okay. So what we're gonna do now here is this. We're gonna go to the iPad, and we're working with the normal probability distribution. I downloaded those notes, so you guys can see that here. And of course, ultimately, what's this? Ultimately, that's odd. Never seen that happen. Ultimately, we're going to use the TI calculator. All right, you guys with me on that? Ultimately, that's what we're doing. Now, remember, you focus on language and process, but you have to know what in the world is the normal probability distribution? What is normal? Just that word in and of itself being normal, right? So we're going to kind of look at this here. Informally, this is called the what? The bell-shaped curve. So recall the type of pictures of data you get when creating a histogram for a frequency table. So remember, originally we created these things. This is a histogram. It's a bar chart. Okay, you guys remember we created that? It was like on your first test even, but it was based on gathering data. And then this is really a picture of data. This is a special picture of data, a special picture. You say, what do you mean it's a special picture? Yeah, how does that picture look to you guys? Remember we asked you questions about the behavior of the distribution. Did it look normal? Did it look, did it look right skew? Was it left skew? Was it uniform? Was it normal? Do you guys remember those ideas? We even looked at box plots and we talked about that. You guys remember that, or am I just imagining it? Yeah, we did all that. But we're kind of back to that, meaning if most of the data is in the center, it's normal. I'll say it again. Most of the data is in the center. This is your histogram. You know, the bars there. Then it's a normal distribution. And that's a special situation. It is so special, we developed a whole chapter to the normal distribution. It's that special. So you're gathering data. You got the special picture where most of the data is in the center, in the middle, around the mean. You say most of the data is where? It's around this mean here. That's where the mean of the distribution is. It's in the center. And then it tapers off significantly as the data values become more extreme. So in other words, the bigger the data values are, the lower the frequency. The smaller the data value, the smaller the frequency. So to the left of that mean mu, where the center of the data is, and to the right of it, you have smaller frequency values. That's what this histogram is showing. And if your data looks like this, we can say that it's what? Normal. And the graph is it's known as informally, aka the what? The bow-shaped curve. You guys ever heard that phrase before? Bow-shaped curve? Yeah. It's the normal distribution. Formally, this is what we call it. But informally, it's the bow-shaped curve. Okay. Now, remember, historically, there's a formula historically. And you go, oh my God, is that the probability distribution? Is that P of X? Yes, and it's what's called a continuous random variable, these X values. We're going to see that. And every normal distribution is based on two parameters. It's based on your mean mu, and it's based on the standard deviation sigma. So this is why you'll see a sigma and a mu, and then, you give the X value, that's a distribution there. And, you can determine a probability knowing those three things, but you're using really, I should say, calculus in all honesty. So if you really wanted to see where some of these numbers came from that we'll be working with in our TI, like the binomial, like the Poisson, you got to take other math classes, I guess. And in the normal distribution, that is specifically the case, that you do need what? I should say. No. We're not we're not going to use the formula. We're going to use the what? TI. So the question is, oh my God, this formula, scary. Actually, it's scarier than you think. You'd have to take calculus too. You'd have to learn how to integrate, and then you'd have to learn how to do numerical integration, probably by Simpson's rule. And then you really can actually do the normal distribution. So what I'm saying is this material is based deeply in mathematics. It just didn't fall out of the sky. And in fact, the statistics course I took, because I never actually took this course, I took a statistics course. I certainly did, and I did a lot of work in probability, but it went beyond what I had to prove everything. I proved it. Stuff we use, we had to prove. It's a different kind of thing. Here, you guys get to use. So in other words, you get to bypass all of that stuff, all that math to get to use it, and they substitute it with the TI calculator is what it is. I wish I had my applause button. I'm going to have to find another way. Okay? All right. So I'm just kind of giving you guys the background. I'm setting the table before we eat. Okay, you guys see what I'm saying? I'm going to have to set the table for you guys. I have to express to you guys what this distribution is, what kind of things are normal, and then how to use it. And we're going to, all you got to know is your left to right and your language. Do you guys know your left side from your right side? Okay, good. Do you guys know about language, like at least, no more than, between? You go, really? The stuff we've been talking about the first day, that language, you even made a worksheet for us? Yes. That's what it is. It's the hardest part for people. Language and what? Process. So that's what we're doing. We're just setting the table, giving you guys the background behind it. Then we get to use the TI. I told you this, in some ways, the course is downhill. You just have to learn how to use your calculator. So let me respond to you guys about this, because I made this whole worksheet for you guys to write notes. What can be represented by the normal distribution? Things that grow what? Naturally. Like a human being. Believe it or not. It's like this first example, I took what? Men. So you see that stick figure? That's a guy. Now, what do you guys know about men? They're supposed to grow how? Naturally. And in fact, you can think of it this way. Every guy is reproduced by nature. You know, what are you talking about? Well, I'm a guy, and there's another guy in this room. He's reproduced by nature too, naturally. A third guy is reproduced by nature naturally, right? And what's the story? Even though we're reproduced by nature naturally, there's going to be some variance. In other words, there's going to be what? If you ever notice about men, what do you guys notice? In this setting, what are we measuring? We're measuring what? The height of what? Men. So have you noticed that even though men are supposed to be what? Reproduced naturally in nature, we have different heights, don't we? Some men are taller and some men are what? Shorter. Is that true? You guys understand what I'm saying? It's like nature reproduces a guy over and over again. Here he is again. Here's another one. Here's another one. Here's another one. The problem, though, is we're not all the same height. But what do we know? We have a mean. That's the typical. That's the average. That mean goes in the center of our distribution. That's why we have 67 inches in the middle there. But we also know there's a certain consistency. The standard deviation, 2.9 inches. So even though men are reproduced the same way over and over again, we do have some differences because not even God and man reproduces the same thing twice exactly the same way. That's deep, ladies and gentlemen. That is so deep. Oh my God, I sit there and marvel at it. I'm going to say it again. God and man can't reproduce the same thing exactly twice. Or I can't really speak for God. Maybe God makes a decision not to do it. So I can't speak for God. But I know, scientifically speaking, every man has a different height value. Every snowflake is different. So what we think of is man and nature does not reproduce the same thing exactly the same way twice. There's going to be some variation. That's your standard deviation, how we measure that. And then there's going to be the typical, the average. But then some people are going to be what? Above average, and some are going to be what? Below average. You guys get the picture? So, and there's nothing special about men. I'm going to say this to you guys. Women can also be what? Reproduce the same way twice, over and over. Reproduce over and over again naturally. And yeah, they can have different heights too, and they do. Okay, you guys understand what I'm saying? And they can have a consistency in their height, and they do. In fact, women's heights are more consistent than men. I think the standard deviation is 2.5 inches. And then the data comes from where? The United States. Why did I point that issue out? Because if you change countries, ladies and gentlemen, what's the story? The average height, yeah, everything's different, meaning the average height of a man is different in other countries. Same thing with the standard deviation. Where do you find, what country are the men tall? Where's my sound effects button? That's note to self. Get your sound effects up and running. I think I might have a button here I can put some music to. What do you guys think? Is there another location in the world where men are a tall height? Anybody know? Germany. Yeah, their average height. I'd like to look it up. I might even be able to find some data on that. I might have had some. Men are tall in Germany. You guys know that? In fact, my grandfather in World War II used to dread, because he fought in Europe. There was anybody know what fixed bayonets are? Yeah, they used to have to say fixed bayonet. Sometimes there's going to be situations where they had to put their knives at the end of their rifle as fixed bayonets. He used to hate that phrase because he's actually smaller than me, I think. We were the same height. So he had to go up against over 6 foot tall men with their bayonets. Fixed bayonets. Oh, anyway. Every time I think of Germany and the height of men, I think of my grandfather and the fixed bayonet story. So you change the population, you change the mean, change the standard deviation. Where are men not so tall? Is there a region in the world where men are actually shorter? Are they sure? Really? 5'6"? Well, in the U.S., it's 5'7". I'm not thinking of Mexico. I'm thinking of Peru. Anybody ever been to Peru? I wonder what the average height of a male is in Peru. We might have to look that up someday. I might look it up. Anybody know, are people smaller in Peru? You don't know? You guys don't know? I think they are. I wonder what the average is. I think they are. Anyway, I have to give you guys that detail because remember, you change the population, you'll change these values. And you can also, if you wanted, gather data worldwide if you wanted that. You could do that too. So everybody's now together, you get the mean and standard deviation there. But, you change the population, you essentially change some of those values. And then here's one of my favorite examples too, because, everybody likes to, historically, when I talk about the height of men, you got all these giggles in the room. You guys know what I mean? You get these giggles and you go, oh, and that Mr. Judge is 5'7". You get all these giggles. And then what example I used to bring up always, okay, you ladies are giggling at Mr. Judge. Let's talk about the weight of women. And then all of a sudden the giggles go away. So there's some history behind the worksheet, It was always funny. I was talking to my buddy about some lectures I used to do with some of the topics. It's kind of funny because he videotaped them back in the day. But anyway, the weight of women. And in fact, this is a typo. Sorry, ladies. The weight of women. This is not in the United States. It's probably more like Japan. Where the ladies have the less weight. Because be careful. Weight and being thin are not necessarily the same things. Okay, not necessarily. They could be correlated. But where do you have the weight of women? What's the average weight? Is the average weight of women in the United States 107.6 pounds? That's the typical height. Can any lady stand up and tell me they weigh the typical height of 107.6? Please stand and let us know. You guys know, see how all of a sudden the giggles go away? So this data might be reflected in what? Japan. Why did I say Japan? Huh? Historically, I think gathering data, Japanese women tend to be very what? Thin. Huh? They're very thin. But also not as tall. So there's you got to be careful. There's also a book out about French women. French women are also what? Thin, but they have a heavier weight, I believe, because they're taller as well. So, there's some variables there, just so you guys know. But, you could look at the weight of women as well, because every lady is supposed to be reproduced the same way, what? Twice. So you go, okay, here's your lady. She's reproduced the same way twice. Has a mean, has a standard deviation. That mean is right in the center, right in here. Okay? There you go. You know what? Here's another one of my favorite examples. Woo! Now this gets a little sensitive. Do you guys know? And this doesn't really come from mathematicians. We don't care about the nature of the physical situation. We only care about the numbers type of thing. But where do you get this idea called IQ? What's an IQ score? Do you guys know what an IQ score is? What is that called? Who do you want to get angry at if you say, oh, IQ score? What's this about? An IQ score is known as an intelligence quotient. That's another way of saying you're able to assign a numerical value to somebody's intelligence. So every person is reproduced in nature over and over again. Every person has what who can you blame? Psychologist has an intelligence and it's measured. That's where the word quotient comes, assigned a numerical value. What's the mean of people's IQ scores? It's 100. Where's the center? In the middle. What is the standard deviation? 15. You guys see what I'm saying? The mean is 100, standard deviation is 15. Everybody is reproduced the same way twice. We're all supposed to have the same intelligence, but we don't. Some people's intelligence are what? Higher than that mean, and some people are what? Lower than that mean. You guys okay with that? But most people are around where? 100. So we all have an intelligence that's supposed to be the same, but it's not. Just like our height is supposed to be the same, and it's not. Just like our weight is supposed to be the same, and it's not. You guys see what I'm saying? But all in theory, you do you reproduce man over and over again. It's all supposed to be the same, but it isn't, because not even man and nature can't reproduce the same thing twice exactly the same way. But if you see the data look like a bell-shaped curve, then it's a normal distribution. And things that behave naturally like these are normal. And it's not unique to people, even animals. Animals have a typical height, depending on how you measure, and a typical weight. Okay, whether it's a horse, and then different types of horses. Even a breed of a dog. You say, okay, I like huskies. Okay. They have a typical height and a typical weight, but they're not all the same. Some are taller, some are smaller, and there's a variance, and there's a mean, there's a center of the data. Anyway, you'll see a bell-shaped curve as well. Okay, you guys okay with that? Any sort of thing that's reproduced in nature over and over again has a typical. All right. And you say, but Mr. Judge, you've been saying man and nature. What do you mean about man? Well, man as well creates machines. And even though you might think, and we have machines that reproduce the same thing twice over and over again, right? There's still a variation. Even in this water bottle, and this is one of my favorite examples. You see this water bottle, what does it say? 500 what? Milliliters of water. So who put the water in? Not man, but a machine. So if you were to actually get all these water bottles and take out the water and actually measure accurately, you guys know what you would find? It all has a different numerical value. It's not 500 exactly. It might be 503.89674, 501.6173. Okay, there's going to be a center, there's going to be a mean of your measurement, and then there's going to be a standard deviation, how consistent that measurement is. But you'll never find exactly 500 milliliters. Trust me on that. It all depends on the accuracy of your machines. And every now and then, when your machines start to, they got to calibrate them because they start to be very, very, very what? Inaccurate. There's a threshold value for the standard deviation. When it exceeds that tolerance, they go in and they actually service the machines so that it could increase the accuracy. So even in manufacturing, ladies and gentlemen, what's the deal? You cannot reproduce the same thing exactly twice. You just can't. There's going to be a mean, there's going to be a standard deviation. It's going to look like this, a bell-shaped curve. So this is another hypothetical, okay? You go, what do you mean? Yes. You see this here? 508.6 milliliters. That's your mean. And then this is your what? Standard deviation. Most of the data is going to be around the center. And X is measuring, the values of the data. Remember, X always represents that data value. So anyway, I'm introducing to you guys. I'm setting the table before we eat about the normal distribution. Again, are we going to use that nasty, ugly formula? No. What are we going to use? Our TI calculator. What do we got to know? Well, we got to know the details behind the distribution, what it is, what it represents, and then we got to know really our left from our right and language. It's an easy thing. It's a lot easier with the TI than it was in the past. You guys are going to see it. Okay, you guys okay with that? All right. Oh, this is another one of my favorite examples. Was it this class or another class? I can't remember. Jesus, what class was it? About pregnancies. Did you guys know about being pregnant? Do you know the duration of pregnancies? And this is for women. Is the mean is 268 days. Did you guys know that? Maybe you did, maybe you don't. We always think of it as 9 months, but 9 times 30 is 270. But there isn't always 30 days in a month. So, that's kind of a weird thing, but that's kind of how we approximate it. That's why this is where they get that 7 months from, or 9 months, sorry. But they're not really accurate. The average number of days a woman is pregnant is 268 days. How consistent is that? You know what the consistency is? Standard deviation? You guys know what that is? Oh, sorry. That's what? That's 15 days. What are 15 days? 2 weeks. So some women are pregnant for less than that, and some women are pregnant for longer than that, right? And then what kind of happens if you're pregnant for a significantly longer time? What does the doctor do? Do you guys know anything about that? The doctor induces a pregnancy. I guess there's reasons why they do that. I don't know. Have to talk to the doctor and ask the doctor, hey, why do you induce a pregnancy after a while? What's the reasons? There's reasons behind it. Okay, so, you might even think, wow, you mean women aren't always pregnant for exactly the same days? Nope. Okay, so you got most women are pregnant for around 268 days. Some could be more, some could be less. Here's another myth. Here's another big myth. What's your body temperature, ladies and gentlemen? What is it? Well, people used to think that the body, the very common myth is that body temp, just like being pregnant for 9 months, but it's a generalization. Another generalization of body temperature is 98.6. Have you guys ever heard of that? Your temperature is 98.6. No, it isn't. Temperature is what? On average, maybe I should do that. Maybe I should get a thermometer. And we'll gather data and because we can do it fast now, right? Oh, maybe I should do that. Get everybody's body temperature. And I can show you guys gathering data. Oh, that's supposed to be a mean mu. I got a typo. The mean is actually 98.2. And what's the standard deviation? 0.2 degrees. So it's not 98.6. Everybody says it's 98.6. 98.2 with a 0.2 degrees standard deviation. So that's your body temperature. Most people are around 98.2. When is your iPhone going to be able to measure your temperature? Soon? So let's go over this, ladies and gentlemen. We're going to go over some facts about the normal distribution so it makes some sense when we use our TI. Okay, this is a big deal. Okay, now, of course, you guys are looking at really the math behind it, but you don't have to learn all this math. It's all in your TI. So what I want to say to you guys is this, that we're going to focus now on the area here. Now, remember, these are supposed to be what? Why is the area here equal to 1? Because 1 is the same as the number 100%. So this picture represents 100% of the data, meaning that's all your data. And you go, really? Is that all the data? Yeah, look at this bell. This bell is all the data. You with me on that? We drew a histogram of all the data represented in a bell. So the area under that curve is really representing the data. That's all the data. So this is why the area under that curve has a sign of value of 1, because 1 equals 100% of the what? Of your data here. You guys with me on that? And then notice something here, because this is going to be an important detail. This is an important detail. We're looking at this picture. If this is 100% of the data and your mean, mu, is in the center of your data, how much of that is to the right and how much is to the left? We're going to use some critical thinking here, ladies and gentlemen. How much of the data then is to the right and how much is to the left? Oh, where's my music? How much is to the right? How much is to the left? Is it 50% and 50%? Does that make some sense? What's a half of 1? 0.5. So 0.5, remember, this is the same as 50% because that is the decimal representation. So 50% is to the left of the mean and 50% is to the right of the mean. Okay, 0.5 is equal to 50%. Okay. So we're looking at this bell. We're going to play a game here. You kind of need to go through this exercise to make sense of this. I call this game, what percent of the bell is shaded? We just already said, and what shade is in blue? We already said that this is what? 100%, because that's all the data. You guys okay with that? And I use the word symmetry. What does symmetry mean? Do you guys know what symmetry is? This word? Are there any artists in the room, by the way? Any artists? No artist? Okay. If you're not an artist, okay, that's fine. Is there anybody in the room who's beautiful? Nobody? Nobody's beautiful? Well, that's what we're told. That's what we're told. But if you were to ask an artist, what's an artist's definition of being beautiful? A face that is what? Symmetric. You say, what does that even mean? If you draw a mirror, ladies and gentlemen, oh, sorry, that doesn't look symmetric, sorry. Oh. Well. Maybe that's a little better. Okay? A face that is symmetric is considered beautiful by artists. It's not my definition, so don't go there. You go, that, Mr. Judge. Artists believe that symmetric faces are beautiful. So I like to use that word symmetry. In fact, not just it's mathematical. And put the mirror here. And you go, okay, let's put the mirror and reflect it. What you see on the left should be what you see on the right. If you do that, then you're beautiful, according to an artist. What's the problem, ladies and gentlemen? Nobody has a symmetric face, but some faces are more symmetric than others. And if it's more symmetric, you're considered what? Beautiful. Okay, so I mean, now everybody's going to look in the mirror as they drive home. And they're going, okay, am I beautiful by an artist's definition? Well, I bring it up because this idea exists in mathematics. It exists here. And what I mean is what you see on the right should be what you see on the left. It's supposed to be symmetric, your bell. And so 50% of the data is here. And then on the other side, it's what? 50%. Because the bell is supposed to be symmetric about the mean. You guys with me on that idea? You guys see the point? Not too bad. It's not too bad. And of course, if you add the left half with the right half, doesn't it equal the total? Okay. Easy peasy, lemon squeezy. Now we're going to get into the game. This is the game, ladies and gentlemen. It's an important part of the game. So what we're really measuring now, and maybe it's not as important as it used to be, but I always go through it. If I ask you guys this question here, what percent of the ball is shaded here? You know what they did? They gave you some information. They said from here to where? To over here. For some value of x, what percent of the ball is shaded there? 38%. That's what they communicated. But what did they leave blank? That portion on the left. What should that left portion be? Uh-oh. What should it be? Isn't that 50%? Is it 50 minus 38? We're trying to find, think of it this way. You got $50 in your left pocket. You got $38 in the right pocket. How much money do you have, ladies and gentlemen? How much? You had 100? No. Well, it is 100 total, but what should it be? Why is it $88? In other words, what percent of the ball is shaded here is really what? It's 88%. Is that right? Because 50% is on the left, 38% is from those two portions. So you're going to have to add. Is that true? Did you guys add those values there? All right, let me do this here. That's an important detail. I just want to point that out. And then I summarize. 50% is on the left, 38% is on the right for the total of what? 88%. So this is a picture of 88% of the ball being shaded. What do you guys think? Is that okay? All right. What about now? What about now? See, remember, we're trying to really get a good idea of what's going on here. So from this value of x to the mean, what did they communicate to you? What percent of the ball is shaded there? They're saying this is 42%. Is that right? How much is over here? They didn't communicate. That's another 50. Good. And you guys know that because that's the right half of the ball. Is that true? So what percent of the ball is shaded? They're talking the total. Well, if you had $42 in the left pocket, $50 on the right, what does that sum give you? What's 42 plus 50? That's going to give you what? Is that 92%? That's what we're saying. So we're just kind of looking at that bow, getting a good feel of the bow. 92% of the bow is shaded in this picture. What do you guys think? Is that hard? No. You can think of money. Every time I think of money, that helps me a lot. What about this picture? What are they trying to communicate in this picture? 42% is in your left pocket. 38% is in your what? Right. So what would you guys say? What percent of the bow is shaded? What's the total? Aren't you going to have to what? Add these, and what do you get? 42 on the left plus 38 on the right gives you 80%. So this is 80% of the bow total that's shaded here. You're adding the area because you're taking the left portion, you're adding it with the right portion to get the whole bow that's shaded in the picture, 80%. Okay, anybody have any questions on that? Easy peasy? Any questions on those? What do you guys think? Is that okay? We got Renata, good morning. We got Brittany, good morning. And we got Monty, good morning. And Tad, good morning. 80% to Tad. Now, I want you guys to look at this picture here. This is different now. This is the definition of what we call a what? A right tail. What percent of the bow is shaded on the right? That's the definition. Why do you think they call it a right tail? Remember I said, do you know your left from your right? Why is that a right tail? It's on the tail end on what side? Okay, easy peasy. Is that right? No big deal. And what do you think they call this picture? That's a left tail, is that right? It's a left tail. Because the tail is now on the left. So notice when you say tail, that goes on forever. So I want you guys to know that's a picture of what we call a left tail. This is a picture of what we call a what? A right tail. It's on the right side, and that goes on forever because that's what the arrow represents. Okay, you guys see what I mean? Anyway, we need those definitions in our language. Ooh, this is one of my all-time favorite questions. Let's see if you guys can figure out what this is. So what are you guys looking at in the notes here, right? You guys looking at this. What they're doing here, first of all, isn't that a right tail? Good. Okay, now what are they trying to communicate? Here's your mean. What are they trying to say? What does this mean here? What are they saying here? Well, I mean, yeah, actually 95% of the whole bow is not shaded. You're right, because over here, yes, that's another 50%. So yes, 95% is not shaded. What are they really saying then? What percent of the bow is shaded? Isn't that the question up here? What percent of that bow is shaded? 5%. Good. That's what I want you guys to notice. Isn't that 5%? So that's 5% of the bow. Is that true? All right. Is it still easy? Well, how did you get the answer? Because there's going to be people in the room. I've been teaching this course for a while in my life. There's people in the room that go, How is that 5%? You know what I think of? Has anybody ever eaten a donut? Maybe people haven't. They don't know what I'm talking about. How's a donut made? Do you guys know how donuts are made? Well, here's what I'm saying to you guys. This here is a donut. You know how they made that? They did what? They started with what? This circle. And you know what they did, believe it or not? You know what they did? They punched a hole in it and they threw it out. So what I'm saying to you guys is, that's how a donut is made. If you don't believe me, they used to. I don't know if they do it anymore. I used to watch them make some donuts when I was a kid, because I used to go to this local donut store. My dad would take me for breakfast. That was one of the best things I ever remember, going and get a donut. I used to watch them make the donuts, and like, oh my God, they took the dough and they punched a hole in it and they threw it out. They took it out. So when you take the hole out, that's thought of as what? You're subtracting. So when I say, how's a donut made, you can think of it this way. They started with what? 100%. And what did they throw out? That 95%? Is that true? This is what you guys told me. 95% is not shaded. But then what's the remainder? What's left? 5%. This is how you got the 5%. So if you were wondering, how did those people get the answer? Because like I said, there are people who are wondering with that. What they did was they started with all of the bow being shaded and they threw out the 95% to get 5%. That's all they did. Is that what you guys did? Did you guys realize that's what your brain did? Isn't that amazing? This picture is describing what your brain is doing. Going back to just making a donut. Man. Anyway, whatever. We don't have to go through that. Okay. What about this picture? What percent of the bow is shaded? What are you guys looking at now? Isn't that a left tail? What would you guys say? Oh, you guys know. Isn't that so? You guys know. How do you guys know that's 10%? Again, what are they saying here? 40% is not shaded. They didn't even tell you about the right side because they assume you know that that represents 50. Isn't that 90% that's not shaded? So 90% of 100%, what do? 100 minus 90 is what? Isn't that 10% in your left tail? What percent of the bow is shaded? Anyway, so these are some of the exercises we historically have had to do. Now, let's see if you're really awake. It's just a mental exercise with what percent of the bow is shaded. So when we work with the distribution, you guys kind of have some good feel. What do you guys think this means here? What does this actually mean right up in here? 44. What does that mean? Well, what that means is that total should represent 44%. But what do you guys notice of the total? Doesn't include, well, it doesn't include this portion. It also doesn't include this portion. You are right. This is not a right tail. Good job. So some of this is missing. Is that true? So what percent of the bow is shaded then? How do you guys know that's 14%? Because you are right, it is 14%. What did you guys do? They communicated that would be 44, and you threw out the donut hole. Is that right? Isn't that the donut hole? What's left? You guys are correct. You guys are good. Good for you guys. Look at that. I told you it's going to be simple. It's 14%. Easy peasy lemon squeezy. Not a big deal. Good job. 44 minus 30 gives you 14%. That's what I did in the notes. All right. What about this picture, ladies and gentlemen? What about this picture? What are you guys looking at now? What does this mean here? Well, what they're trying to say is from here, right, to here, what does that measure? 36%. How much is missing? Well, what is that? You guys know? 36% would be from there to there. And you're right. You might say, but Mr. Judge, this is all, we don't want pink. This is not a left tail, is it? What percent of the bow is shaded? What does this give you? What's 36 minus 24? What is this? That's 12%. Is that true? That's 12% of the bell. So 12% of the bell is what? Is shaded. So I even put that in the notes. 36 minus 24 gives you what? 12. Right? What do you guys think? Is that pretty good? All right. So we're just setting the table today, ladies and gentlemen. We're going to set this nice table for us about the normal distribution. And let me give you guys a definition here. Okay? Definition here. This is a very special distribution. You want to know what we call this one? What does it say? It's a standard deviation. I'm sorry, it's a standard normal. This is the definition. If you have a normal distribution and the mean is what? 0. And the standard deviation is 1, what do we call this? This is going to be our definition of the what? Standard what? Normal probability distribution. The mean, what is your mean? The mean is 0, and your what? Standard deviation is 1. Bless you. It's called the standard normal. Just to let you guys know. And we represent that standard normal with the letter what? Z. So I'm going to say this is the letter they use to represent the standard normal. Z. Also called the Z distribution. We're going to make use of that in our future as well. So you guys know the standard normal. It's called the standard. It's under the hood for everything that we do, or at least it used to be. When you had to use the formulas and tables in the past, we don't have to use any more tables, ladies and gentlemen. We're going to use what? TI. All right? You guys know what I'm saying? We don't have Z table anymore, but it used to be there. I got to introduce it to you guys. Oh, introduced. There it is. So what I'm saying is, on my website, the formula card, you're going to see this Z distribution, this table. And this table was always good for finding the percent of the bow that's shaded from 0 to some Z value. This is the standard normal distribution I just talked about. Also called the Z table here. Okay, so we're saying, the Z table. So if some of you guys took this course in high school and you go, oh my God, a Z table, what is that? Well, this is what they're referring to. They used to use tables to answer questions. And this is what the picture is. This is the Z table. So I used to have to show people how to use a Z table. I used to have to show people how to deduce an answer with area, like I just went through. and your table. So it was a process. And we get to skip the process because we're going to use a TI. So if you guys remember from high school, you go, oh, I used to have to use a Z table, Mr. Judge. I'll say, yeah, it's the older way, I guess. Now we have technology, a TI calculator. We get rid of the table. In fact, the people that made the table had to take calculus, and then they had to take a numerical calculus 2. It's a whole thing. And this stuff we used to have to go through. We don't have to go through anymore. But what I want to remark about here is this. This is what you guys really need to know now. Okay? I'm going to introduce you some fundamental information of what you guys need to know to be successful here. This is all before we do an example. Do you guys know what this is a picture of? What is this a picture of? You ever seen this before? This is called the real number line. R for what? All real numbers. The real number line. Okay? And in the center, you have 0 on the real number line. Is that true? What do you guys know about numbers? Now I'm going to have to use some colors here. The numbers to the right is 0. What do you guys know about those numbers? Do you guys know? This is where all the positive numbers live. Those numbers are to the right of 0. Is that true? Do you guys know what I mean? And then, I don't know what color. Pink? Pretty in pink. Those numbers are what? To the left of 0. What are those? The negative what? Numbers. Negative numbers, and what are these? Positive. You guys okay with that? What do you guys know about 0? 0 is what? It's neither positive nor negative. 0 is neutral. Okay, you guys okay with that? So this is the general picture of your real number line. Easy peasy, lemon squeezy. You guys remember this from algebra? Right? The class they say nobody needs. Because people live perfectly happy lives without knowledge of algebra, according to some politicians. You're perfectly happy without knowing about numbers. Because who needs them anyway? Anyway. This is, again, we're going to take a closer look. Because this is the details we need. A closer look at the real number line, okay? So yes, this is a real number line. 0 is neutral. It's not positive. It's not negative. Positive numbers are to the right of 0. Negative are to the left. Now, I want to see if you guys know something here. I'm going to put here the location of number A, and I'm going to put here the location of number B. You with me on this? Here's A and B. Real number line. Which number is larger? Which is the larger number? A or B? How do you know? How do you know B is larger? In other words, I'm going to write down this fact. Remember, JAWS opens to the bigger number. A is less than B. How do you guys know that? What's that? Larger numbers are to the what? Right. So the further to the right you go, the bigger the number. Does that make some sense? Do you guys know what I'm saying? All right. So that's one fact. Fact, this is the S portion of the course, by the way. You say, Mr. Judge, what's the S? This is a supplement portion. This is the portion we assume everybody knows, but that's not the case anymore. Yeah. Larger numbers live to the right. And also, what does that even mean? Smaller numbers are what? Are to the what? To the left. So I want you guys to really, really understand that. Maybe you already know, because you know about the real number line. The further to the right you go, the bigger the number. Further to the left you go, the what? Smaller the number. I always used to say to students, remember, larger numbers are to the what? Maybe we got to colorize this. Bigger numbers, larger numbers. I don't know what colors. I'm out of colors. I don't know what to use. What do we use up here? Oh, we use golden. Here's B. It's bigger. Here's A. It's what? Smaller. Larger numbers are on the what? Are on the right side. Smaller numbers are on the what? Left side. So, for example, like I said, here's kind of some things we're probably going to have to know. Okay? If you have to write down the numbers, what? 120 and 108. To plot those numbers here on the real number line, really just looking at a closer look. We don't care about zero. We don't care about negative. All you want to know is what number is larger and what number is smaller. Does that make some sense? How do I describe this? I'm going to have two locations, here and here. Tell me now, using the closer look at the real number line, what number is on the left and what number is on the right? Because remember, I said people have to know their left from right. Smaller numbers are on the what? Left. Larger numbers are on the what? Okay, so what's on the left? What's on the right? There you go. Easy peasy lemon squeezy. You guys with me on that? No big deal. Is that true? Okay, you guys get that? What if they said 65 and 32? Because I found from my experience, with some of this stuff, this is what people need to know. So now look at these two numbers. One's going to be on the left. One's going to be on the right. Which number's on the left? Which number's on the right? Why? Larger numbers are to the what? Right. Smaller numbers are to the? Do you know your right and left? Oh, shoot. How did we learn that? I still remember how I learned it. How did I learn it? Miss Snodgrass, when I was in elementary school, Miss Snodgrass, you know what she used to do? Because I didn't know my right from my left. So this is what Miss Snodgrass did. She got a ribbon, because I guess I missed the day they talked about right and left. I showed up. I was absent the day they did right and left. Miss Snodgrass. She said, Daniel, which one's your right? Which one's your left? I was like, I don't know. So she got a little ribbon. And she goes, what hand do you write with? It's a different word. Right and right are different. It sounds the same. So it's confusing. So what hand do you write with? She put the ribbon on it. So all day I walked around with a ribbon on my finger to remind me that this is my what? Right. And then the other one was my left. That's to this day. Right, left. Miss Snodgrass taught that. I don't know how you guys learned it, but stop and think. How did you learn it? Huh? I don't know. See, that's the problem with teaching and learning. Is that people just say, it just is. It's not just is. There's a way to learn, and there's a way we learned it. And sometimes I have to go back and think, how did I learn it? I write with my right, that means the other's on my left. You know who gets messed up? People that do both. What do you tell them? You scratch. Is there a hand you prefer to scratch with? You scratch with your right. I don't know. Or do you scratch with your left? Yes.
What I learned is that you take your fingers like this.
Right.
And your left hand makes an L.
Oh, there. See? Again. Again. But what if you're dyslexic? I'm dyslexic. And people are dyslexic. This is what I'm telling you. In my experience, I have a lot of experience teaching. I got a communication from a student who doesn't like being in class. Her student doesn't like being here. But why? I feel lonely. What do you mean? You just lecture. I don't get to know my other students. Oh, really? That's the problem? There's a lot I learned I have to deal with, ladies and gentlemen. There's a whole spectrum and a rainbow of things I have to deal with. These are some. Some students don't know their right and their left. And so when you work with the normal distribution and you go, this is what you do. What's on the left? What's on the right? They're just numbers. That's where I say language and process. So there's a challenge with language. There's a challenge with process. This is helping to address the what? The issues of what? Process, knowing your left and your right. What is lower? What is upper? What is smaller? What is larger? Where do the larger numbers go? On the right. Where do the smaller numbers go? On the left. That's it. That's it, ladies and gentlemen. So I have to deal with a spectrum. Are you any of you guys lonely? You guys need to talk to your neighbors? Don't laugh. I have made an observation my whole life. There are people who can't do anything unless the person next to him tells them. Do you guys know what I'm talking about? It's not a learning issue. It's something different. It's a what? Yeah, it's like an emotional issue. It isn't a learning issue. It's a what? It's emotional. You know where I actually observed it for the first time in my life? Because I even remember that. There's a lot of things I don't remember, but I don't know why I remember this. I remembered it in elementary school. I remember we got instruction in elementary school from Miss Snodgrass again. And Miss Snodgrass says, okay, class, get to work. You guys remember those phrases? Okay, class, get to work. Now you got to work. Okay, I'm going to get to work now. So Miss Snodgrass goes, okay, I told you what to do. This is what you do. Okay, class, get to work. So, okay, I get to work. And remember, we used to be paired next to, we used to sit pairs in a desk. So it was a 2-person desk, pairs. And they always had to switch the pairs up because kids would start talking and they get squirrely and okay, let's mix you guys up. And so I remember next to me, I remember I was getting to work and I had a buddy next to me and he's just sitting there. I'm like, hey man, psst, get to work. Miss Snodgrass says get to work. You got to get to work. And he's just like, no. What? Well, why not? Why aren't you going to work? You say, I wanted to come help me. I'm like, what? You can do that? And go, why? He goes, I like when she helps me. Is that a learning issue? Or is that an emotional issue? What is it? Sometimes people want what? Someone to the left of them to say, this is what you do. That's what I've noticed, even in elementary school. So the kid, it wasn't that he just felt more emotionally he needed that emotional connection. Maybe he didn't get it at home. Because I've thought about that. Maybe it just wasn't an emotional connection at home. Person needed to come to school and get that emotional connection. That's all. That's all. Nothing Nothing more than that. What do you guys think? Is that maybe the possibility? What do you think? And for some people, that's what the issue is. It's more of an emotional thing. It's not even a learning thing. It's a, can I get by that that emotional attachment I need with some other human being? If you can, here's what I say. If you could recognize the problem, then you could work on fixing the problem. You see what I mean? So if you recognize, you go, Mr. Judge, I need that emotional connection. This is why I need someone next. Because through my years, I've always seen that where a student would not want to ask you a question. They rather ask the person next to them a question. Hey, how do you do this? Hey, I'm over here. What? Stop it. What's going on? And they would rather what? Ask the person next to them. It's an interesting thing. So I say, if you could notice the problem, that's when you start to get used. That's when you can fix the problem. Does that make sense? And that's true not just about learning. That's true about everything. Maybe you got a drinking problem. And you got to change that. What's the only way you can do that? You got to notice there's a problem before you ever get to trying to change it. Yeah, it has to be real. That's a real problem. It's no different. So you guys can use all of this in your daily life, no matter what it is. Anyway, tomorrow, what are we going to do? We're going to work on a normal probability distribution question, and I'm going to remind you, left, right, lower, upper. And if you can do that and put the language together, then you're good to go. All right. We'll see you guys when? Tomorrow.